what we have covered so far. If not, we are looking at how to calculate the fugacity of a component in a mixture, equivalently how to calculate this departure function for any component I in a mixture. Because why we want this also evaluated at the same temperature, pressure and mole fraction. Because it will turn out that we saw that for instance when we take the pure component, we define the fugacity as P times exponential of now. So this is the departure function we want at the temperature to determine why this is important, and then we used it for establishing the criterion for equilibrium, or using the criterion for equilibrium for the vapor liquid phase coexistence. The fugacities of the two phases become equal. You can easily show that because the fugacity of the first phase is the pressure times the chemical potential minus the ideal gas chemical potential evaluated at temperature and pressure by RT. Now the second phase, everything is the same, so the temperature and pressure are the same. Right? However, if for instance we define the fugacity in this manner, F star, not what fugacity is. I can always define it in terms of the departure function with the T and B specified. You can easily show that F star 1 will not be equal to F star 2 because the specific volumes of the two phases are different. So when you are evaluating mu minus mu Ig at the temperature and volume, so the liquid phase it will be the temperature will be the same, the volume will be the volume of the liquid, whereas for the vapor it will be the specific volume of the vapor, and the two are different. So that's why this is important. Even though we might get it from this is important. Now, when you come to the fugacity of a component in a mixture, the issue is a little bit more complicated. The fugacity of a component in a mixture is defined as P times Zi exponential of importantly both quantities, that is the chemical potential of the actual mixture and that of the ideal gas mixture, must both be evaluated at the temperature, pressure and mole fraction of the mixture. Right? However, here though you can again define an alternate fugacity which is evaluated at temperature and specific volume of the mixture, which is what we are going to calculate first. Before we get to this. Now, if I have equality of the chemical potential, because this is alone is equal, we are not worried about the other quantities. The equality of the chemical potential of the two phases, does it imply, suppose we have two phases, liquid and vapor and equilibrium, all of them, both of them have C components, right? Now, is the fugacity of a component in a mixture, phase 1, is it equal to that in phase 2? The answer is not very obvious because on top of the temperature and pressure which are equal, we have the mole fractions which are anyway different for the two phases, unless you have an acid group or something where the mole fractions are the same. Right? So the proof is not as straightforward, it is quite straightforward, the proof is not as obvious. So what if I like calculate this for phase 1, I have to put the mole fraction of phase 1. But then the ideal gas mixture also will be evaluated at the composition of phase 1. So there are 2 points where the composition of the mixture comes in, one here and one here, you will see that the two will get cancelled out. So I'll leave that as a proof for you, and maybe we can take that later. But so that is why, and the fugacity. So now if I define an alternate fugacity, which is evaluated at a specific volume and mode fraction, you can show that those two fugacities will not be the same. But however, this can be shown to be, it is quite easy to prove that. I'll let you, we have done so many of these derivations, you should be able to prove it. I'll leave it as an exercise. So that is why we are interested in the departure function, evaluate constant temperature and mole fraction. The fact that the mole fraction of the two components are different for the two phases is not going to affect the equality of the fugacities of the components. Okay. So now this can be written as integral 0 to p. Both expressed as a function of a dummy variable p prime and at a fixed temperature and mole fraction or mole number, it doesn't really matter as we will see. So now if I do this, we have already got these expressions to deriving the properties of ideal gas mixture. We saw what this is. This is nothing but integral 0 to p pi pm minus RT by p prime, right? As a function of p prime. So now if you see, compare it with the mu minus mu I here, Tp, you will see that this can be expressed as p minus RT by p. Whereas this is PIPM. So again, the formulas are quite, there's an analogy in that the specific volume is replaced now by the partial molar volume. Now, if I want to, so this is nothing but dV by dNi, expressed as a function of the pressure and so on. But what we want is, so again you see that we get the Ni into the picture and not the mole fraction. Right? So now dV by dNi, and then I have the integral over pressure. So obviously I have to now invert this and express P as a function of dV and the mole numbers, and you have to do the integration by parts and so on. It's a somewhat lengthy procedure. You can consult any book which will have a derivation of this type. But however, I am going to do something different, which I believe is easier, and that is I will directly approach it, not directly, indirectly approach this, but by first calculating in the dV, and now I introduce the mole numbers rather than the mole fraction you will see white. So this can now be written as integral infinity to the volume d prime. So now to calculate, we saw to calculate d mu I by dp and d mu I by dt at fixed p and z. We use the general equation, this equation, to arrive at that, and we showed that this is related to the partial molar volume, whereas the derivative of mu I mixed with respect to temperature at fixed pressure is related to the partial molar entropy, so it's a negative of that. But now to get the derivative with respect to volume, keeping T and N fixed, this is keeping T and N fixed, it's also keeping T and N fixed. I have to obviously look at this minus dV plus so now from this I can, this is now for the mixture, so this is for the mixture, so we can easily see that since mu I mix is now dA by dNi. What I want is the derivative of that with respect to V. So if I try to do that, is equal to d by dV of dA by dNi. Right? So obviously this dA by dNi is giving dV and nj not equal to I fixed. So when I differentiate that with respect to V, it is giving d and n fixed. Right? I'm not going to write that. It's very clear from the context. This can now be written as d by dNi of dA by dV. dA by dV is minus P, so I get minus dV by dNi. So now what is the same for the ideal gas mixture? Now for the ideal gas mixture, it is the same formula that we hold, right? But P of the ideal gas mixture is sum over J equal to 1 to C Nj times RT by P. So what is dV by dN? I'm sorry, RT by V. So what is dV by dNi for the ideal gas mixture? RT by P plus Nj N1 plus N2 plus N3. So all the other mole numbers won't give anything. The derivative is 0. When I differentiate with respect to Ni, dNi, this is again the delta Ij will come in. And this is clearly equal to RT by V. So if I now substitute that, I will get that has a negative minus dV by dN. Sorry, which implies dV by dNi for the ideal gas mixture is RT by V. What I mean is the negative of that. The negative of that is minus RT by V. So there is a minus already there. So if I can rewrite this as RT by V prime minus dV by dNi, I will make this explicit. Express as a function of V prime, P and N, dV prime from infinity to the actual volume of the mixture. So in one stroke, I have gone, everything is now in terms of the volume. So what about this dV by dNi I have to calculate? Now, so far, we always looked at the pure component, we expressed it as a function of V and T. But we know that it can also be written as a function of capital V, T, and then the N would come in. So just take the ideal gas mixture. So it's most convenient to write it in terms of temperature of a specific volume. But however, if you want to write it in terms of the total volume, right? So V is nothing but V over N. So this becomes nRT by V. This is for the pure component. For the mixture, same thing holds. Obviously, for the mixture also, the pressure is only RT by small p. But however, if I want to write it in terms of the mole numbers, then the total volume will also come in. And then I have that, right? So I can easily do that. For this, take the van der Waals. Now, how would you write the van der Waals for the mixture? It would be V minus V mix minus A over V square, and then V mix is a function of the Z. A mix is also a function of Z. So V becomes a function of V, T and Z. That's the most natural way of writing. The pressure is an intensive variable. It's dependent on the specific volume, temperature and mole fraction. However, to actually implement the departure function to the chemical potential is convenient because this requires the pressure be now expressed in terms of the mole numbers and the total volume. It's very easy to do. All I have to do is simply wherever small v is there, I put v minus v divided squared by n squared. Now what about B and A? They are also in terms of the mole fractions. I know that if something is in the form of mole fractions, I can easily convert it to mole numbers. Just make explicit the mole fraction. It is Zj would be Nj by the total number of moles. Right? So I can easily do that. So it's very trivial to express the pressure, and this is not going to be equal to d by dzi of P. It's quite a different quantity here. So it's a bit difficult to establish a relationship between dP by dzi, giving B, T and the other mole fractions fixed, and dP by dni. But this is what comes out to be very useful when you calculate the departure function. Now we are not done yet because I want the departure function at temperature pressure. And I can now make this also in terms of mole numbers. Doesn't matter because it's going to get fixed. Mole numbers are kept fixed and the mole fractions are also automatically fixed. So it's not going to make a big difference. Right? So now what I want is this, that the two are not equal. Right? So to find the difference between the two, so I have to now do a similar thing that I did when I calculated the entropy departure function. I pointed out that either you calculate S minus Sig dP directly, or you calculate S minus Sig dV, but note that it is not equal to that evaluated when temperature and pressure are fixed, and just add the additional quantity. Right? So in the same way now, so now the mixture, I am going to denote it, the mixture quantities are the pressure, you can just going to call P, I am not going to call P1 or P2, P. The mixture temperature is P, the mixture volume is P, and the mixture mole number vector is N, and I will call this N1 to Nc. So now, I am now comparing these two. So I have ui mixture, ui mix, right? Evaluated at temperature, pressure and Ravi potential versus ui mix evaluated at temperature, volume. And the important, most important that I didn't mention, the P is so the pressure, volume and temperature that I expressed must satisfy the equation of state for the actual substance. Now there are four quantities here. I can compare this and this, and I can also compare this and this in the two expressions. So now the familiar question, is this equal to or not equal to each other? The mu I mix evaluated Tp and N is the same as that evaluated Tp and N or not? We have to go back to the question we asked for the pure component. Are the two the same? No. So that means I haven't made things clear. Probably the pure component also. The answer is wrong. The two are the same because the point here is that the pressure, temperature, volume and mole numbers all correspond to a single state. Now I can either choose the pressure, temperature and mole number or the volume, temperature and mole number. It doesn't matter. I only have to go to a different function. Either I express mu I in terms of Tb and N or in terms of Tp and N. Both of them are corresponding to this is a single state. The state that I am looking at is characterized by a pressure P, a volume V, a temperature T, and a mole number N1, N2, Nc. Right? So whether I evaluate it using the temperature, volume, and mole number, or the temperature, pressure, this is a crucial point. They are all the same states. It is like I introduced two functions for the pure component, right? Right? So as long as P is equal to the two quantities are the same because they correspond to the same state. So the pressure that is there here is the pressure corresponding to the volume and temperature. Maybe it is a bit confusing here because there I use the specific pressure, temperature and mole number. Here I am using a general variable mainly because I don't want to, because as it is you have N1, N2, Nc. If I use P1, P1, it may appear as if I am down the pressure of a particular component or the temperature of a particular component, which doesn't make any sense. I want to avoid, we are going to have to deal with that notational problem, but here I wanted to avoid. Right? So I just put the pressure, temperature and volume of the mixture as P, E and V. So the two are the same. If you can't understand this, it's very difficult for me to explain any further. You have to think about it and convince yourself. The two are the same. But what about the ideal gas mixture? Clearly that is now going to be different. Just as the ideal gas evaluated at B1 and T1, chemical potential, and the ideal gas chemical potential evaluated at T1 and T2 were different. You have to go back to that arguments and figure out why we argued that the two were different. So now this I have established. So all I have to do is, right? So if I want this, I write it here. So this is what I want. Minus what I want. Now I can write this. The first term, I can write it as PV and N. If you want, I can put this as a cap and I can put this as a bar. So I am using a different function. Chemical potential can be expressed as either as a function of temperature, volume and mole numbers, or temperature, pressure and mole numbers. So as long as the set TVN corresponds to the same state as the set TVN, I can choose which function, either the cap function or the bar function to use to determine the chemical potential. They are going to be the same, provided the states are the same. And this ensures that the two states are the same. The pressure I am talking about, the pressure evaluated at the given volume, temperature and mole number. So that is what I have to do. So I have put this as a bar and let me make this also. Now what I want, so I have what I have here is mu I ideal gas mixture evaluated at TBN. I already have that formula for that difference. So obviously I want to introduce that. What I want is this difference. So now what do I have to add and what do I have to subtract? What do I have to add? What quantity I have to add? It is not done because what I want is this difference. Now I have written a different difference. Now to complete, what should I put plus? Whatever I have written there, right? Plus minus what? TB and N. So clearly, we are going to show that these two are actually different. Because now for the ideal gas mixture, I have two different states. One corresponding to the temperature, volume and mole number. Another corresponding to the temperature, pressure and mole number of the actual substance. Even though the two sets of variables correspond to the same state, for the actual substance they will not correspond to the same state for the pure component. So let's now write, we have the expression for the idea. Now I have to be very careful. All of these correspond to the this is the function I am going to use. Everything corresponds to IGM. Right? So now if I have to evaluate, let's first evaluate the quantity this. Let's first evaluate this. This is the easiest to evaluate. So now what I am saying is, what this means, this is actually mu I cap because this is what I have directly. All corresponding to the ideal gas actual mixture, the P of the ideal gas mixture is equal to the P of the actual mixture. The mole number vector of the ideal gas mixture is the mole number of the actual mixture, right? Which means that is yi is the mole fraction corresponding to the specification of the mole number. Now the two tests will come for your understanding. Suppose I want to calculate this. Now what would you do? So let's now work with this equation, right? Let's work with this equation. I will show you both ways, right? Work with this equation. So I am given only the cap. I am going to use that only. So now in this, T mix is equal to T ideal gas mixture is equal to T. V ideal gas mixture is equal to V, and N ideal gas mixture is equal to N. So what is P ideal gas mixture equal to? nRT by V, not this RT by V. This nRT, sum over A1C Nj times RT by V. And this is what I have to substitute for. Everything else remains the same because these two, this is specification 1, this is specification 2, they are quite different for the ideal gas mixture. One is the temperature, pressure and mole number correspond to the actual temperature, pressure and mole number. Here the temperature, volume and mole number of the ideal gas mixture corresponds to the actual temperature volume. So now if I am constrained, there are two options. Either I can convert it to a bar function, which means I have to eliminate the pressure and put here nRT by V. That also you can do. But I stick to this. I want to deal with just one expression. But now I am saying that the pressure here really corresponds to the pressure of the ideal gas mixture. At the time when we introduced the expression, we didn't have to make this distinction because it was obvious we are discussing only the ideal gas mixture. So it's automatic when I write something like this, I don't have to say that this corresponds to the temperature of the ideal gas mixture, this corresponds to the pressure of the ideal gas mixture, that corresponds to the mole fraction component I in the ideal gas mixture. It's understood. But here now, because I am now calculating the ideal gas mixture properties based on a state specification to the actual substance, right? Then I have to make the distinction. So what I do, I have the cap function. So I have to put only the pressure of the ideal gas mixture. So I now look at this. P of the ideal gas mixture is T. So what is this now? So this is now going to be, for this specification, the mu I IgM is going to be first term mu I naught of T. That remains the same because the temperature of the ideal gas mixture is equal to the temperature of the mixture. Now let's come to the last term. That is also the same because the temperature of the ideal gas mixture is equal to that of the actual mixture, and the mole number vector of the ideal gas mixture is also equal to the same mole numbers as the actual mixture. So that mole fractions are also not going to change. Now what about this term? So RT remains the same. The pressure has to be log of nRT by V. So this is the ideal gas mixture chemical potential of a component I evaluated at T, V and N. So what is this difference? This difference clearly is now, right? So the difference is, so let's write that difference. It's going to be mu I naught of T with RT log yi plus RT log nRT by V minus the one that I have calculated here, mu I naught of T with RT log yi plus RT log V. So that is where the difference comes in. So the difference clearly is RT log nRT by dV. Because the P would come in the denominator. So what we are getting now is that the chemical potential departure function that I want can now be written as the first term is given by this integral infinity to V and then we have plus RT log nRT by dV. This is actually the compressibility factor of the mixture. So you're getting an additional term plus RT logarithm Z, which has to be included into the expression for the departure function. So the two departure functions are not the same. We now go back and compare with mu minus of dV of the pure component, you will see that the two are not, one cannot be inferred very easily from the other. Now, I just want to write that. If I have that, I will write it quickly. Actual forms are not important. What I have here is this is one of the longest expressions. So dV minus RT minus RT log Z. We do have that. I hope that we haven't made a difference either in the sign. This RT log. Oh, I'm sorry, this is correct. This is not Z, this is actually Z inverse. So we will get minus RT log Z. So that at least matches. So this is RT. So this whole thing can be written as minus RT log Z. Right? So I can write this as minus RT log Z of the mixture. Now this also has a minus RT log Z. That's the only similarity. These terms I don't have for the departure function for the chemical component of the potential of Earth. And then I have infinity to V, E minus RT by V prime, dV prime. So the only similarities are in this and in this. Instead of P, I have dV by dNi, and of course I have this, but I don't have any of these terms at all. So what this means, what I am trying to point out, that why I said that for the specific properties of the mixture, the departure H minus HIG can be directly inferred from the corresponding formula for H minus HIG. Such an extension, you will run into error if you arbitrarily try to infer the chemical potential or any partial molar property departure function from the corresponding property of the pure component. So you have to be careful. You have to re-derive everything and then figure out how they compare. You cannot just directly write those expressions. If it were possible, I would have simply followed and written it from here. But you can see there is no equivalent for dV by dNi in the pure component. Right? So you won't easily extrapolate. So now, how to calculate this is the only question now. This is the only part from the equation of state. Of course, Z also has V, so that means when you are given dV and Z, you would have to go and calculate that V. Right? When you are given dV and the mole number or the mole fraction, you have to go and calculate. So let's now calculate dV by dNi. You look for the van der Waals equation of state and see how it looks like. Right? So dV by dNi for the van der Waals equation of state. That's what we are going to erase this. So I will take P to be equal to RT by terms of M and the total volume. So I can write this as nRT by D minus NB mix. Just multiplying both numerator and denominator by N. N is the total number of moles. Minus N square A mix by V square. Now it will be easier to actually calculate the derivatives of these with respect to Ni. That's why I am writing it together. Now, what is dV by dNi? Right. I am taking now a particular mole number. So, one would be first, this would be RT by V minus NV mix times the derivative of N with respect to Ni. What is that? Derivative of N, capital N, with respect to Ni. 1. Plus nRT, I will differentiate this. It will be minus actually V minus NV mix square. That's a derivative of that. Now I will differentiate. Right? So this is very important. dV nj not equal to I. So I don't want you to calculate dV by dNi and put it as partial molar volume. It is not proper. Because temperature, volume and all the mole numbers other than the one I have picked are to be kept constant. So V minus N V mix, I have to now differentiate. So 1 over V I converted as minus 1 over V square, V minus N V mix square. So I will now differentiate this with respect to Ni. Right? So that would be minus D NV mix by dNi. So I can remove these minus signs. And then minus, this is capital V. So now I have minus 1 over V square, V by dNi of N square A mix. So that is where the N dependence is. There is no independence in V. Because V is a variable, independent variable in this whole expression. You have to keep that in mind. So I have now got this. So this is really first term. So I have to write it clearly. RT by V minus NV mix plus nRT by V minus NV mix square times V by dNi of NV mix minus 1 over V square V by dNi of N square A mix. So obviously this NV mix has to be expressed as a function of all the C mole numbers. We will see that it is quite possible to do that. Right? So if we do that here, so now you can see to complete the calculation of it. This is that. So I have to calculate this and then do this integration, and then I have the term subtracted or added. Now you see that I have already calculated, this is the only calculation. Now I see I have to calculate two more derivatives. D by dNi of NV mix and D by dNi of N squared A mix. Those of course now depend on the, so there are two aspects to it. One is the actual equation of state, another is the mixing rule. The two are independent of each other. I can use a Van der Waals equation of state, right, and use a different mixing rule. So the formula stands as it is, but now for that particular mixing rule I have to calculate these derivatives. On the other hand, I could have some other equation of state, but the same mixing rule, in which case the formula I am going to derive now will apply for the mixing rule, but the other terms would be different. Right? So now the formula that I am going to derive applies to the particular mixing rule I have chosen, which is that V mix is sum over j equal to 1 to C Bj Zj, and A mix is sum over I equal to 1 to C, sum over j equal to 1 to C Aij Zi Zj, where Aij given by square root of Aij. This is the mixing rule, and for this this mixing rule, I am going to derive the two derivatives. So now n being mixed, you clearly see now is I take the n in and I can multiply Zj by n each term. So each Zj will be multiplied by n, so it becomes nj. So this simply becomes sum over v into 1 to c bj nj. Now what is d n d mixed by d ni? dni. J is a summation index. And bi, right? So this is clearly bi. A way of more formally writing it is simply differentiate this. And we know dnj by dni is delta ij. If you want that additional step, I can write that. And you can clearly see sum of j equal to 1 to c bj delta ij is bi. So you remember dnj by dna, if you're not sure how this is coming about, dnj by dna is delta ij. So now, what about n square a mix? Now, I have n square, I can take it into the sum because it's a constant factor. So each term will be multiplied by n square. One of the n I can use to multiply zi and I get ni. And the other n I will use to multiply zj and I get nj. So very conveniently, this becomes now again differentiate with respect to we have to be a bit careful. So I'll make it k because I picked one ni that I'm going to differentiate. There are c choices. So I'm not picking that and calling it ni. So I cannot use I as the summation index. I'll make it akj. Zk, zj, so become akj, nk, nj. So because ni, I am giving a special status to a particular mole number. So I cannot use that also as a summation index. It will lead to some confusing answers, right? So certainly I can write it like this. Now I differentiate with respect to ni. This is a bit complicated. So again I will take the derivative inside. Because derivative of sum is sum of derivatives. So I take the inside and then when I look at this I will simply differentiate term by term. Right? So there it will become derivative of product is I have to apply the product rule. So akj times dnk by dni times nj. The akj is a constant plus nk times dnj by dni. So then this will become sum of, I am going to write this as two separate sums. The first sum would have akj, dnk by dni is delta ki or delta ik, doesn't matter, times nj plus sum over k into 1 to c, sum over j equal to 1 to c. akj, nk, delta ij. These are going to simplify and clearly, right, I can shift the sum. But first I would like to do the sum over, I look at this, so delta ik will simplify everything. Right, so first I can do the sum over k. So I will write this as the first term I am going to write sum over j equal to 1 to c. The first term nj, sum over k equal to 1 to c, akj delta ik. J is also there, but it will be part of the sum. So I am not tampering with the sum, I am just writing it differently because we want to get rid of the delta ik because that is going to simplify considerably. Now the second one, now I see that I have delta ij, so obviously I would like to do the sum j equal to 1 to c first. So I will write this as plus k equal to 1 to c in j. Then on top of it I have some j equal to 1 to c akj delta delta ij. So what is sum over k equal to 1 to c akj delta ik? It's a sum over k. J and I are not changing in the sum. J and I are fixed for this sum. So again the terms with k runs from 1 to c, only for the term k equal to I will there be a quantity. All other terms will be 0 in that sum. Right? So what will you get? Aij. Right? So the first term is sum over k equal to 1 to c nj aij plus sum over k equal to 1 to c mk and ak. This is j equal to 1 to c. So j, I'm sorry, akj is missing. So this is now j equal to 1 to c. So this is going to be clearly aki. So I have two terms. Now we have run out of time. Are these two terms equal or not? Equal. Why are they equal? Yeah, summation term is there. That is one point. I can always make this I equal to 1 to c ni. No, j equal to 1 to c nj aji. But then the other point is aij is equal to aji. For both those reasons, because this is only a dummy index. So I can first thing I can do is to simply make this also j equal to 1 to c nj aji. Because k is only a summation, because I can use anything except I can use anything. Here, just look at this sum alone separate. Right? This is a separate sum. So I establish contact with this. This is also j equal to 1 to c nj aij. This is sum over j equal to 1 to c nj aji. But here, by definition, aij is clearly equal to aij. So I can write this finally that d by this term can be easily seen to be 2 times sum over j equal to 1 to c aij nj. Considerably simplified and what we might have thought. Right? So I can put that together. Now I have everything in place. I have to put the whole thing into this integral and then integrate it along with RT by V. That will complete the formula for the random. We'll see how to handle other equations in tomorrow's class.